We're going to become aware of basic facts of what's called an Argand diagram, or basic facts and skills to do with the complex plane. So firstly, an Argand diagram is basically a geometrical representation of complex numbers. So we're drawing them. So it's a geometrical representation of the complex plane. So all possible complex numbers can be drawn using an Argand diagram. Okay, in one of the forms anyway, because later on we'll learn polar form and that will look different. Now hopefully you'll see that we have what's called isomorphism, or basically complex numbers, or the Argand diagram. The things we see on that are isomorphic, or corresponding to two-dimensional vectors. Which in turn use aspects of the Cartesian plane. So we have our axes, and instead of labeling them I and j, or x and y, or whatever, I guess we shouldn't label them I and j, but instead of considering directions I and j, unit vectors and so on, or x and y, we've actually got real and imaginary. So for complex number z, we have rez and imz, real and imaginary. So for z being complex number, the real aspects of any complex number z is represented on the horizontal axis, and imaginary is represented on the vertical axis as shown. So if we have z1, 2 plus 3i, and if we have our scale as such, we would have, if we have 1, 2, 3 and so on, and 1, 2, 3 as shown there on the other axis, 2 plus 3i can be shown in two ways. It can be shown as a dot, alright, or a point, and we call that z1. Okay, there's a second way of showing complex numbers. If we look at a similar one, complex number, whoops, I'll call it z2. z2 is 1 plus 2i. The other way these can be shown would be, you do the same thing, you'll go 1 across and 2 up, but we can also write them a bit like a two-dimensional vector. And sorry, I didn't mean to have an arrowhead on there. Usually they're not represented with an arrowhead as a vector would be, but you can see it can be in a line form or just as a point as such, and they're both common geometric representations of complex numbers. So that's how you represent a simple complex number when it's in this form, and again there'll be more forms in the future, but in that form that's how you represent it on the Argand plane. One more, or one more of each type. Let's say we've got z3 and it's negative 2 plus I. So negative 2 plus I would be there, and that would be z3. Let's do one last one, and we'll put it in the line format. So z4, hey, let's use the only quadrant we haven't used yet. So let's say we've got negative 3 minus 2i. So negative 3 minus 2i there, and that would be z4 in the line format. Should be a straight line. Okay, z4 as such. Now an operation, multiplication by a real number, so which I've called k here, it's isomorphic to scalar multiplication of two-dimensional vectors. Sorry, I shouldn't say two vectors, it's 2D vectors. So it's really the same. So it corresponds anyway. So if we have the complex number z1 there written as 1 plus I, z1 there, and that would have a length. Now that's length is called a modulus, by the way. modulus. In fact, that's probably important to copy down. So basically, just ignore the brackets. It's actually not a side note. It is important. So that's that magnitude symbol that you'd see in vectors, or the absolute value symbol you might see with numbers. Well, modulus means the same thing. It's essentially the length of a complex number on an Argand plane. It has those same but 2 bars either side. And for Z1 there, it's root 2. Now, if we multiply it by a real number, we have triple basically the length, so the modulus becomes 3 times. So that will be the modulus there of 3Z1. So 3Z1 has a modulus of 3 times the original complex number. So if we drew it, its length would be 3 times the length. So such out to there. Okay, so it works the same way as it does on 2D vectors. So let's look at the sum and difference. Really, if we can do the difference, the sum's even easier. So you might remember when you did 2D vectors for the first time and you learnt vector addition, head to tail, and then you learnt subtraction, which is adding the negative of the second vector. So it works the same way if we want to geometrically show the sum and difference of complex numbers. So let's have a look at that on an Argand diagram, because we've already looked at it in the forms down here. And we don't put the arrowheads, but as it is the same process, and I'm using a line format, these could be represented just as dots too, by the way. And if we have the negative, if we're subtracting Z2, it's like adding the negative of that, which essentially is like 1 minus 3i on the end of Z1 here. So we go to the right by 1, and then we go down 1, 2, 3, and there we would end up. So basically, if we can call, if we let Z3 be let Z3 equal Z1 minus Z2, just helps call it something. Z3 would actually would be there at 3 minus 2i, okay, because it's at 3 minus 2i. And just showing with the way we've done it in the past, Z1 minus Z2. Okay, let if Z3 equals Z1 minus Z2, we've got 2i plus the negative of Z2, which is negative 1 plus 3i, and that's basically minus negative 1 is plus 1, so that's 2 plus 1 is 3, and we have I take away 3i is minus 2i, and you can see that's why we get that result there. It's even easier with summing complex numbers. It's just like 2D vectors. Just don't use arrowheads as a general rule. Now there's a special property of multiplying what happens when you multiply a complex number by I. It's actually the rotation of a complex number anti-clockwise about the origin. So what happens is that if we multiply a complex number by I, so if we have Z and we have Z multiplied by I, so sorry, I meant to call it Z1, so Z1, and we multiply that by I, it rotates it 90 degrees anti-clockwise about the origin. Okay, so 90 degrees anti-clockwise. Let's have a look at that. We can do that algebraically as well. If we have so let Z1 equal something easy like 3 plus 4i. We can show it algebraically first. So if we have doesn't matter which way you multiply by Z, but if you go Z1 times I, you have 3 plus 4i multiplied all by I, we have 3i plus 4i squared, which is I squared is -1, a -1 alert there, so that would be -4 plus 3i, and let's show that. So we have 1, 2, 3 plus 1, 2, 3, 4i, that's where z1 is. I'm just going to show in point form to be different there, and basically the resultants there, let's call that z, let's call it z2, so we can put it on here. So z2, according to this, should be, sorry, my axes haven't aligned with the grids properly, I apologise for that. So we've got -1, 2, 3, 4, and plus 3i, 1, 2, 3, 1, 2, 3, and that has happened. So if you have a look, okay, so I did add the lines in the end, and we've got a 90-degree anti-clockwise rotation there. And look, they're the same length because if you define the modulus, it's no surprise we're going to use Pythagoras' theorem. So it'd be 3 squared plus 4 squared square root for the modulus of z1. So, and if find the modulus of z2, Pythagoras, okay, and it'd be basically -4 squared plus 3 squared. They both come out as 5. So that, yeah, it's just a rotation anti-clockwise. So you just multiply by I for a 90 degrees anti-clockwise rotation. Just quickly, we could show it with one more. So if we got z3 is -1 minus I, we might be down here. And then if we multiply that through by I, we get 1 minus I, and that's down there. And basically, we've got our anti-clockwise rotation there. Finally, there's a special conjugate property too. So if we have conjugates, generically, if z1 equals a plus bi, and the conjugate of z1 is a minus bi, there's a special property on the Argand diagram. They're reflected in the horizontal axis. So if that's z1, the conjugate of z1, so if we go across a and up b to get z1, to get the conjugate, I'll put in a different color. We go a minus bi, so we go across the same, but we go down the b instead, so that would be down there, and lo and behold, we have a reflection in the horizontal axis. Okay, some properties of Argand diagrams.